So this is going to be a review of Marking Period 2, final exam packet. Now, Marking Period 2, we talked about functions quite a bit. We spent some time talking about linear functions, and we talked about solving systems of equations, which we were finding the intersection of two lines. Then we talked about a few other functions like absolute value functions and greatest integer functions, and then we started talking about polynomials and quadratics a little bit towards the very end. So this first problem right here, which of the following is a linear function? Well, let's first investigate the answers that are not linear functions. So if we look at B, it's not linear because its degree is 2. Linear functions have degree 1. Now, letter C here also has a different degree. It has degree 3. And if you look at D, that's an absolute value function, which is not linear. So A is the answer because it's x to the first power. It's allowed to be multiplied by or divided by a constant term, but that is linear basically because it's x to the first power. There's no variables in absolute value or square roots, and that's about it for that one. Number 2 here, describe the transformation from x squared, the parent function, to x plus 3 squared plus 1. Well, don't forget, technically there's parentheses around this x right here. So all the transformations to the input to x happen on the inside, and it happens in an opposite way. Here's the idea. If you plug in 0 for x here, what x value would I now have to plug in to get 0 on the inside now? -3. That's why this actually moves to the left 3. And then everything on the outside affects the y-coordinate, so you can see we've added 1 after we square, so it goes up 1. So this would go left 3 and up 1. Number 3, you're solving an absolute value equation, so the first thing you want to do is isolate the absolute values. So just pretend this whole thing is the variable and get that by itself. And then once you get here, you got to think, well, the absolute value of what numbers could equal 6? Well, either positive 6 or negative 6. So we take the inside, x minus 2, and say if x minus 2 equals 6, this will be true, or if x minus 2 equals -6, this will be true, and then we solve each equation. The reason why you don't change this to x plus 2, you might be thinking, because you're taking the absolute value, is because we're not actually taking the absolute value, we're discussing what would have to be inside the absolute value before we take the absolute value, such that what comes out would be 6, and that would be 6 or -6. So this is really where the change of sign comes from. Another strategy for this problem, because it's a multiple choice math test, and this is a solve problem, is don't forget that you can use these answers and plug them in and see which one gives you true statement. Remember, you'd have to plug in both answers here, and they'd both have to give you true statements for it to be the solution. And this is a strategy you can use on the SAT as well. So let's scroll down a little bit here. Number 4, we're doing some function notation. So just remember how function notation works. This whole term right here is a y, and it's just notation. There's no actual math going on over there. It's explaining what's happening. And just look at the difference. This was f of x, this is f of 0. So it's literally telling you what to do by how it changed. The x is now 0, so all you have to do is plug in 0 for all the x's over here. Now just remember that when you plug in 0, you should recognize when I plug in 0 for x, that's going to give me the y-intercept. And when you have a polynomial function like this over here is always going to be the y-intercept. So when they ask you to plug in 0, they're actually asking for the y-intercept, which is -8. So I really didn't need to plug in the zeros here, but that's technically what it's telling me to do. Number 5, we're plugging in -3. The biggest mistake people make is a calculator error on this one. They'll either not put parentheses around the -3 and square it, in which case, over here, the -3 and square it, in which case your calculator will not handle it the way you want it to handle it, and it'll come out a negative number when it shouldn't come out negative when you square it. The other mistake people make is that they put the 2 inside the parentheses. Remember, the multiplication by 2 comes after the squaring, so the parentheses should only be around the -3. Now on the graph, this is actually less stressful than up here. It's actually quite easier. You just got to understand the notation. This is saying find f of 1. Remember, f of x was the original, so this is f of 1. What happened? X changed. Now we're not actually using this function now. We're looking at this graph, which is over here. And this is what we're calling f of x right now. But that was what the notation was. So look, x is 1. So it's asking you when x is 1, what's the y-coordinate there? So we go over to 1 for x, go on to the graph. What's the y-coordinate of this point right here? And you can see the y-coordinate's -2. This is asking us when x is 0, what's the y-coordinate? Now it's actually, remember, when you plug in 0 for x, it's asking for the y-intercept, which is right here. So -3. Now this is actually asking the reverse. Look, x isn't filled in. You're trying to figure out what x is. This is actually saying if when y is -4, what's the x coordinate? So go down to y equals 4. Sorry, y equals -4, and it's this point right here. And what's the x coordinate there? -1. So that's why that's the solution there. Scroll back up. Well, which one of these is linear? Well, we already talked about this. This is quadratic. This has variables multiplied together, and this has a variable in the denominator. Remember, 1 over x is basically x to the -1 power, so it doesn't have an exponent of +1. And this has 3 to the x to the first, 7y to the first, all the variables to the first power, and they're allowed to be multiplied by constant. To find the x-intercepts, all you do, and this goes for any function at any time, you plug in 0 for y, and then you solve for x, and that's how you get the x-intercept here. How do you find the y-intercept? We already discussed this. Plug in 0 for x, and that goes for any function at any time. And you get y equals 18/5. Yes, you're allowed to have fractions in math. Which of the following lines are perpendicular? Remember, you're looking for slope that's negative reciprocal. So probably one way you can do this is just get y by itself and look at the slopes. Check out these slopes right here. This is 2 over 1, so they're reciprocals of each other, 2 over 1 and 1 over 2, and they're also opposite signs, so they're negative reciprocals of each other. If you look at A, these have the same slope, and that means those lines would be parallel. So let's roll down here. So state whether it's a function or not. Remember, a function, here's the idea of a function. It's the idea that every input will only have one output. So that means that no x value will plug in, and sometimes it'll come out one number. Sometimes when you plug it in, it'll come out a different number. It has consistency. Now on the graph, how that manipulates itself is that there should be no points that have the same x coordinate on the graph. If that happens, it's going to create a 2 points vertical of each other, so you have the vertical line test. So if I draw a vertical line right here, you can see it would intersect the graph at more than one point, therefore not a function. If we look at this mapping right here, every x value only goes to one y value, so this is a function. Even though 2 and 3 go to the same y value, they're only going to 1, and that's why it's a function. And if you look over here, every x is matched with exactly one y, so this is a function. Again, 1 can go to 6 and 2 can go to 6, but if I added another point here of 1 and say 7, then that wouldn't be a function now because it has 1 going to 6 and 1 going to 7. So in its current form, this would be not a function. That is completely unnecessary. I don't like this program very much, but it's getting the job done for now. So if we want to graph this, notice it's linear, so it's a line. So there's a few ways you could do that. One way is to get y by itself, and then you could use the slope and the y-intercept. But another way is just to find the x and the y-intercept. Remember, to find the x-intercept, you'd plug in 0 for y and solve for x. To find the y-intercept, you'd plug in 0 for x and solve for y. And then you can plot those 2 points. Here's the x-intercept, here's the y-intercept, and then just draw a line through those. Scrolling down here, this is already, one too far. This is already in slope-intercept form, so just start by plotting the y-intercept up 1, and then slopes rise over run, so we're going to go down 4, right 3. Of course, you could always also go up 4 and left 3, but we usually go to the right is easier to graph. Scrolling up. We already did that one. Here's 16. Now this is a linear inequality. I can tell it's an inequality by the inequality sign, and anytime there's an inequality, there's going to be some sort of shading or region of answer, as opposed to just say a point. So you're going to graph the boundary line. So you could get y by itself and graph this line. Here we found the x and the y-intercepts again and graph the line. Now it's going to be a dashed line because it's strictly greater than, and that means the points on the line are not actually part of the solution, and we designate that with the dashed. Now if this was or equal to with the line underneath, then it would have been a solid line because points on the line would be part of the solution then. So there's a couple ways to do it. One way is to pick a test point. Now 0, 0 on this graph is right here. And what you do is you plug in 0 for x and 0 for y, and you get 0 is greater than 6. Now you ask yourself, is that true? Is 0 greater than 6? And the answer is, no, it's not. So therefore, since 0, 0 is on this side of the line, it gave me a false statement. I shade the other side. Now, had this been a true statement, like let's say 6 is greater than 0, then I would have shaded the side that contains 0, 0. Another way to do this is kind of put your hand on the line and which way is above the line because it's greater than, and that would be up here. So it's saying where's the y coordinate bigger, which would be up above the line. So that's another way to think about it. Now 17 and 18, we're using our transformation. So first thing you have to do is recognize the parent function. Now this double bracket here is greatest integer function. This is a function that rounds down whatever number is inside. So here the parent points for this are down here. 0, 0, 1, 0, 1, 1, 2, 1. Remember, these are going to be a step function. So this is the beginning and the end of the first two steps. So the beginning point would be closed and the end of the step would be an open circle. So I'm transforming those. Let's look for transformations. Starts with what's inside the greatest integer function. You can see it's still x, so nothing's changed from the parent. So all these x coordinates are still the original point. Now, what's happening to the y? Everything on the outside. It's 2 times minus 1. So it's going to be 2 times y minus 1. So go to these parent points here, plug in these coordinates for y, and you can find where the new steps are. So really the two steps that I originally graphed off of those points are here and here. But then I could figure out the pattern and fill in some more steps to fill this graph. There's actually more steps I can fit in here, but we'll only ask you to graph 4 on the final. So you can see the pattern here is right 1 up 2, and that's what we're doing here. So here we have absolute value. And to find the parents for the absolute value, just think about taking the absolute value of the x coordinates from -2 to 2. What's the absolute value of -2? 2. What's the absolute value of -1? 1. What's the absolute value of 0? 0. Absolute value of 1 is 1. Absolute value of 2 is 2. And try not to memorize the parent points, just try to understand that the parent function's absolute value of x, you know it's a v, and just go plugging in -2 to 2 and taking the absolute value to get the y's. Now let's figure out the transformation. On the inside here, you can see that we've changed from x to x minus 3. That's going to shift the graph to the right 3, so x plus 3. Remember, the inside's always opposite. On the outside, we have 2 times the absolute value plus 1, so 2y plus 1. So I can use these points down here and just plug the y's in. So that is the multiplying by 2 is on the outside, so it's a vertical stretch by 2. Plus 1 on the outside is up 1. And minus 3 on the inside, I'll move it to the right 3. And you can see on number 17 there was a vertical stretch by 2 as well. So here we have another transforming parents. This one's quadratic, you can tell from the squared. So just think about plugging in, oh look, we got a little efficiency going on here. Think about plugging in -2, -1, 0, 1, and 2, and they're going to have the same y coordinates because squaring will make the number bigger, but also everything should come out positive. Now let's see what transformation's in here. We're multiplying the inside by 1/2, so again the inside's always opposite, so that's going to be 2 times x, a horizontal stretch by 2. And then the minus 3 on the outside is moving it down 3, y minus 3, so then just change those coordinates. Going to go a little bit faster here. Square root of x minus 5 plus 2, parent is square root of x. The x of the parents are just your first 3 perfect squares. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. And this one shifted right 5 and up 2, so x plus 5, y plus 2. Remember, the biggest mistake people make graphing this is they go through this point over here on the end, and they make it look something like this, which is not right, because the domain's restricted here to x values greater than 5, because I plugged in an x value less than 5 here, then this would be a negative number, which would be imaginary, and this is the real plane, so it shouldn't show up. Number 21, vertical translation 3 up, you're just adding 3 to the outside, so just add 3 here, and that's where you get the 12 from. What's the vertex here? Well, remember, think about it. This was just shifted to the left 5 and down 7. So which one shifted left 5, down 7? This one right here. This is another problem where you could plug in -5, -7 and see which one actually came out, or plug in, plug in -5 and see which one would come out -7 for the y of the vertex. That's another way you can use your strategies here. Horizontal translation 6 to the right. Remember, that's going to be the opposite on the inside because it affects x, so it's going to be x minus 6. That was unnecessary. I didn't need to show that. Anyway, what else we got? Up here. Okay, now we're doing systems of equations. So in elimination, remember the idea is we want to have try to get either x or y to have the same coefficient but opposite signs. So if I was multiplying the top equation by 3 and I wanted to eliminate y, so that would make this positive 24y, so I want this y to be negative 24y. Well, it's already negative, so just multiply by 4. This is a system of inequalities, so this is just like the one we did already. which is up here. Sorry about that. Where was I? Okay, so you're looking for the overlap of the shading here. But since this is a multiple choice question, you can kind of see that the equations are the same. You just kind of got to figure out based on solid versus dashed and where the shading is. For example, y is greater than x minus 1. You can see this line right here is x minus 1. It should be dashed, but they're all dashed. And it should be above that dashed line. So it's definitely greater than. So it's either A or D. And if you look at the other line, it's solid, so it's got to be or equal to, and that between A and D, that's the difference, so it's got to be A. Which is the ordered triple to the system below? Let's see. Let's come down a little bit. Sorry. Okay. On a multiple choice system of 3 variables, the best thing you can do is just plug in for x, y, and z and see which one comes out true. Now, just because it comes out true in the first equation doesn't mean it's the solution. It's got to be true in all 3. In general, on these 3 variable systems, when you solve them, what you're trying to do is get from 3 equations with 3 variables down to 2 equations with the same 2 variables. So if I was solving this one, I would eliminate z. And then I would probably multiply the middle equation by 4 and add it to the third equation to eliminate z again. Alright, scrolling down. Let's see. Solve by substitution. When you're solving a system by substitution, the concept is you want to get any variable you can by itself. There's 2 good options here. You can get x alone in the first equation by just subtracting 27. That's what's done in this solution. But equally as easy, you could have just divided x by 2 here to get it by itself and divided 28y and 34 by 2 as well. So you substitute in for x in the other equation, then you solve for y here. Once you have y, you plug back into one of the originals, or over here is even the best place to plug in for y to figure out what x would be, which is negative 3. 28 you're trying to solve by elimination, so there's a couple ways to do this. Just make sure first, you can see this one's a little tricky, that x and y aren't lined up on top of each other, so make sure you do that first. Then it's fairly simple to solve this. You got to multiply both equations, so decided to eliminate x here by multiplying the top equation by 2 to make this negative 6, the bottom equation by 3 to make these positive 6. They eliminate, solve for y, and plug in to one of the originals for y to solve for x. Number 29, it's another shading question to a system of linear inequalities. Again, graph each inequality individually, and then just find where the overlap is. You actually have to do that here because it's open-ended. Number 30, here we're solving a system of 3. So, we have to pick which variable we want to eliminate twice. It's fairly easy to eliminate z here if you just add the first equation to the third equation, which was done here. Now I have to use the second equation because I haven't used it yet. And it's very easy to just multiply the top equation by 3 because that'll eliminate z again. Once I have my 2 equations with 2 variables, then I'll just use elimination again on that. Then I'll get y, then I'll take y and plug it back into one of the 2 variable equations to get x. Once I have x and y, I go back to one of the originals to solve for z. Scrolling up here, we already did 26, 31. You can see that, just see which way it's shifted. Normally, absolute value function would be centered at the origin. So first, see where the vertex moved. It moved down 3. And to the left 2. So it moved down 3, so that means it's either B or D. And it's moved to the left 2 because, obviously you can see it's moved left 2, but it's x plus 2 because think about it. If you plugged in x equals negative 2, that would make the output be 0, and that's where it would have moved to. So it moved left 2, opposite on the inside. You think it moved right, but it's actually moved left, and this is the same as the other. So that's the second marking period.